Hello everyone, I'm Muhammad Aqeel from University of Verona, Italy. Today I'm going to present our paper which is accepted at ICCV 2025, titled as Towards Real Unsupervised Anomaly Detection via Confident Meta-Learning. Let's start from the introduction. We argue that what is commonly referred to as unsupervised anomaly detection is more accurately described as semi-supervised anomaly detection, as it implicitly assumes that all training samples are nominal. While this approach alleviates the need for labeled defective samples, it still requires an operator to carefully curate the training dataset to ensure that no anomalous samples are present. This manual filtering step introduces a significant limitation. It is time-consuming and susceptible to human error and bias. Even a small number of defective samples in the training set can lead the model to misclassify these defects as nominal, reducing its ability to detect true anomalies. Additionally, the assumption that all training samples are nominal does not hold in many real-world industrial applications, where undetected anomalies may be inadvertently included in the dataset. A graphical representation of this phenomena is shown in Figure 1. Figure 1 shows the impact of anomalies and near-boundary samples in the training set. In supervised learning, positive and negative samples contribute to determining the boundary between the two data distributions. In semi-supervised learning, often improperly called unsupervised, the lack of positive samples lead to overestimate the covariance of the nominal samples distribution, resulting in a higher number of misdetection at inference time. Our confident meta-learning approach allows models to be learned properly in unsupervised learning by assigning low confidence weight to sample close to and beyond the decision boundary. We propose a novel training strategy that eliminates the need for manually filtering training data. Our method enables deep learning models to learn from raw uncurated datasets where nominal and anomalous samples may coexist without requiring explicit labels. By relaxing the assumption that all training data are nominal, our approach allows anomaly detection models to operate in a truly unsupervised manner. This not only reduces the burden of data annotation, but also improves the model's adaptability to real-world conditions and enhances robustness against data distribution shifts. We achieve this by leveraging a soft confident learning approach that dynamically estimates the reliability of training samples at each epoch based on the current model parameters. Samples exhibiting low confidence at a given epoch are assigned lower weights in the subsequent gradient updates, reducing their influence on the learning process. Figure 2 shows some confidence weights at the last training epoch. Training samples nominal and anomalous for some classes of MVTec-AD dataset with the associated confidence weight estimated by our method. Weight close to 1 indicate prototypical samples, while lower weight suggested samples close to or beyond the decision boundary. The main contribution of our paper can be summarized as follows. We propose CoMet, a novel training framework that allows anomaly detection model to learn more robust models by assigning low confidence score to ambiguous samples near the decision boundary. Models trained with CoMet achieve higher performance in anomaly detection by significantly reducing undetected anomalies at the cost of slightly increasing false positives. Extensive experiments on 3 public benchmarks demonstrate that CoMet achieves state-of-the-art performance, effectively handling the presence of anomalous samples in the training. Here is the CoMet pipeline. A pre-trained feature extractor transforms input images to feature maps if required by the anomaly detection model of choice. Features are then divided into disjoint tasks. In the meta-learning inner loop, one task is used for training and all the other for testing. Losses for training and validation are passed to the soft confidence learning module to compute the model confidence that is used for regularization of the weight update. Once all tasks have been processed, the SCL module uses current parameterization to compute the confidence of each sample data and use it to weight data in the meta update step. The goal of the soft confidence learning module is to allow the model to rely more on those samples that are more prototypical for the nominal class and less on those samples that are anomalous or close to the boundary. To this aim, we quantify both model uncertainty and data uncertainty within an unsupervised learning framework where we do not have access to labels. We will then use these uncertainties to estimate coefficients used in the training phase. To quantify data uncertainty, we adopt the concept of the confidence join from the confidence learning framework to our unsupervised setting. In this context, we consider the relationship between data points and their confidence scores assigned by the model. We notice that the anomaly score reflects the confidence of a model parameterized by theta to predict xi. Since we lack true labels, we use this confidence score to assess the uncertainty associated with each data point. We map these scores to weight to be used in a soft confidence learning framework using a saturated inverse function of the confidence score, as shown in the equation 1 on this slide, where 3 is the threshold defined according to the interquartile range. If we define Q1 and Q3 the first and third quartile of the distribution of the confidence score, a theta x, respectively, the threshold t defined as the second equation in this slide, where kappa is a parameter that can be tuned to best suit the data characteristic. We can now define the data weight loss function as the third equation on this slide, where LADXI over theta is the individual loss function of the anomaly detection model of choice. We quantify the model uncertainty by calculating the determinant of the covariance matrix formed from the training and validation loss distributions. This approach aligns with the statistical method that interprets the determinant of a covariance matrix as a measure of the volume of the spread in multivariate space, with larger values indicating greater variability or uncertainty. Let L-train and L-validation represent vectors of the model training and validation losses respectively. The covariance matrix is defined as the first equation on this slide. The determinant of equations serve as a scalar measure of the overall variability between training and validation losses. High values of determinant indicate significant variability, suggesting high model uncertainty. Low values instead reflect consistent performance, indicating higher confidence in the learning process. To incorporate this measure into the training procedure, we introduce an adaptive regularized term lambda that adjusts dynamically, where lambda 0 is the base regularization coefficient and gamma is a scaling hyperparameter controlling sensitivity to the model uncertainty. This adaptive regularization allows a model to impose stronger regularization when uncertainty is high, promoting better generalization, and to relax regularization when the model is learning confidently. Combining both model and data uncertainty, our soft confident learning loss function becomes as shown in the last equation of this slide. To enhance the model ability to efficiently adapt to the new data with sample confidence, we incorporate model-agnostic meta-learning into our unsupervised framework. The MAML algorithm shown in figure 4 consists of 2 optimization loops. In the inner loop, we update the model parameters to fit a specific task using gradient descent sets with a learning rate alpha as shown in the figure in the equation 1 on this slide, where L train theta is the training loss on the current task. In the outer loop, we update the original model parameters theta using validation performance across the remaining tasks with meta learning rate beta as shown in the equation 2 on this slide. This two-level optimization enables the model to learn which parameter updates generalize well, effectively learning sample-specific weight while balancing confidence-weighted updates with generalization performance. We integrate the derivative loss function from the short confidence learning into the meta-objective, as shown in the last equation of this slide, where theta prime are the adaptive parameters from the inner loop. LADXI over theta prime is the individual loss for data point xi using parameter theta prime. Wi are the weight based on confidence scores calculating using theta prime, and lambda summation prime is the adaptive regularization term. Now let's move to the results section. We extensively validated our proposed approach on three challenging public benchmarks. We report results on MVTec-AD dataset, VIADUCT datasets, and KSTD2 dataset. We use two anomaly detection models, normalizing flow-based differentnet and simplenet, and the performance of different models improved 94.9 to 99.2, 76.2 to 83.5, and 91.5 to 94.9 for MVTec-AD, VIADUCT, and KSTD2 respectively. And for the SimpleNet, the performance improved 99.6 to 99.7, 87.1 to 90.3, and 91.7 to 92.2 for MVTec-AD, VIADUCT, and KSTD2 respectively. The table 1 shows the precision, recall, and F1 score of these two methods. As you can see, the MVTec-AD, VIADUCT, and KSTD2, the performance for different net, the F1 score improved from 84.9 to 92.9, 74.2 to 83.4, and 89.2 to 90.7 respectively. And for the SimpleNet, it is improved from 98.5 to 98.8, 88.6 to 89.9, and 81.0 to 81.2 respectively. Noise robustness. We finally tested the robustness of the model when subject to increasing level of noise in the input data. Noise is defined as the number of anomalous samples included in the training set. Figure 5 reports IOROC performance for noise levels ranging from 0 to 10%. We report comparison against both differentnet and SimpleNet baselines and two robust anomaly detection methods, IRP and MLDIR, that are specifically designed to address this kind of scenario. Besides being the best performing among the different alternatives, CoMet also sustained high IOROC with minimal degradation when noise intensity increases up to 10%. To conclude that we target the problem of unsupervised anomaly detection where unlabeled nominal and anomalous samples are available at training time. We presented CoMet an innovative framework for training anomaly detection models that integrate soft confident learning with the meta-learning to iteratively refine decision boundaries by dynamically identifying and downweighting ambiguous boundary samples. Extensive experiments on industrial datasets demonstrate that CoMet achieves state-of-the-art performance, significantly improving recall without compromising precision. Moreover, its ability to operate effectively on noisy, uncurated datasets make it highly adaptable to real-world industrial applications. These results highlight the potential of CoMet to advance unsupervised anomaly detection, paving the way for more reliable and scalable defect detection. That's all from our side. If you need further details, you can reach us by this email or by scanning this QR code. Thank you so much for listening.